Hello everyone. We begin with module number 5. First topic is on determinants. In this video, we study the properties of determinants. With some examples, we'll try to understand these properties. We'll study the properties of determinants. The first property says the determinant of the identity matrix is always equal to 1. We know that the identity matrix I is defined as, I'm taking a dimension of 3 cross 3 matrix 1 0 0 0 1 0 0 0 1, and determinant of I is equal to 1 into 1 into 1, that gives you 1. Hence the first property is proved. First property says determinant of the identity matrix is 1. The second property says the determinant changes the sign when two rows are exchanged. We'll try to evaluate this property. Let us define a matrix A. We'll take this matrix as A, B, C, D. When I take the determinant of this A is equal to AD minus BC. Let me interchange the two rows and let me define a new matrix as B, that is CD AB. When I take the determinant of this matrix, B is equal to CB minus AD. When I take a negative sign out, I am going to get AD minus BC. This is equal to minus of determinant of A. Hence the second property is proved. We say that when we interchange the two rows, we are going to get when we take the determinant, the sign changes. The third property says if two rows of A are equal, then determinant of A is equal to 0. We'll try to understand this property with an example. Let us take A is equal to AB, AB. So determinant of A is equal to AB minus AB, that is equal to 0. Hence the third property is proved. We'll try to extend the third property to the columns. Now, third property says that when two rows are identical, the matrix determinant of that matrix becomes 0. We'll extend it to columns. When two columns are identical in a matrix, when we take a determinant of that matrix, it turns out to be 0. We'll take a matrix. First row elements are sin square x, cos square x, 1. Second row elements are cos square x, sin square x, 1. Third row elements are minus 10 value 2. And now we have to get the first some modification, column modification we have done here. And the first column is equal to first column plus the second column. That is sin square x plus cos square x equal to 1. Cos square x plus sin square is equal to 1. Minus 10 plus value is equal to 2. Here you can observe that two columns are equal, that is column 1 is equal to column number 3. Therefore, the determinant of this matrix is equal to 0. We'll try to evaluate this matrix. This matrix A is given by 1 into 2 sin square x minus 12. It is minus cos square x it is my plus 2 minus 2, it is plus 1, it is 12 minus 2 sin square x, that is equal to 0. That you can observe here. It is 2 sin square x This will get cancelled out with minus 2 sin square x, minus 12 and plus 12, and this is cos square x, it is plus 2 minus 2 equal to 0. So therefore, this property is verified, which says that two columns, if they are found to be identical in a matrix, then the determinant of that matrix equal to 0. Try to understand the second example. We need to find the value of unknown x given that this matrix is equal to 0. So we'll try to find the determinant. It is given by x into 5x minus 2x and minus 2, it is 2x plus x, and the last one minus 1 is equal to 4 plus 5. So that is equal to 0. Now we'll try to get it. 5x minus 2x is 3x, 3x square minus, it is 3x into 2, 6x minus 9 equal to 0. When we simplify this using the calculator, we get the value of x equal to minus 1 and x equal to minus 3. The fourth property is the determinant depends linearly on the first row. Let us take three matrices A, B, C of same dimensions. First row of A is a linear combination of first rows of B and C. So we have taken two matrices, B with A, B, C, B and C with A dash, B dash, C, B. And the first row first rows of two matrices B and C are added in order to get the matrix A. So determinant of B gives you AB minus 3C. Determinant of C gives you A dash B minus B dash C. Now determinant of A is the determinant of B plus C will give us A plus A dash into B minus B plus C dash into C. That will give you AB minus BC, that is the determinant of B, and A dash B minus B dash C, that is the determinant of C. So we can say that the determinant depends linearly on the first row. Linear combination usually involves two operations. One is called as adding the vectors, other one is called as multiplying by a scalar quantity. Adding the vectors in the first row will give us A plus A dash, B plus C dash, C, D. The sum of can be written as sum of determinant of two matrices A, B, C, D and A dash, B dash, C, D. That is equal to sum of the determinant of B with determinant of C. And the second one is multiplying the matrix by a scalar quantity. We have the first row being multiplied with the scalar quantity C. So we have CA, CD, CD. That gives you CAD minus CBC. So we can take the common term out, C. So we have determinant of ABCD. So it is C into AD minus BC. That will give us CAD minus CBC. Fifth property says that subtracting a multiple of one row from another row yields the same determinant. Determinant is not going to change when we subtract the values of one row from the other row. So let us say that A minus LC, B minus LD and C and D. The C and D are multiplied by L and we have subtracted it from the first row values. So A minus LC into D minus B minus LD into C. So that will give you AD minus LCD minus BC plus LBC. That gives you AD minus BC, because these two terms will get cancelled out. We will get AD minus BC, which is as good as the determinant of the matrix A, B, C, D. Let me explain it in a better way. We will take a matrix here. Let the matrix be A, B, C, D. Now we will do some modification, row reduction, row modification. A minus L into C, B minus L into D. I am multiplying the second row by L and subtracting it from the first row. So whereas the second row will remain as it is. So when I take it A minus LC multiplied by D minus B minus LB multiplied by C. That gives you AB minus BLC minus BC plus LBC. So these two will get cancelled out. So we are left with AD minus BC. That is the same as determinant of the matrix ABCD. Therefore, we can say that if you multiply one row with the value scalar quantity and subtract it from the other row, determinant of that particular matrix will not change. Sixth property says that if A has a row of zeros, then determinant of that A will be equal to 0. For example, we'll take matrix A is equal to say AB and 0, 0. Second row I have made it as 0. Let me take the determinant of this. This will give you A into 0, 0, B into 0, 0. So you get this as 0. Next property is if A is triangular, then determinant of A is the product of A11, A22 up to ANN, the diagonal entry. Let us take an example of a 3 cross 3 matrix. This is a triangular in nature. We have the diagonal elements as A11, A22, A33, and we have the upper triangular. We have the values, entries are there 2, 3, and 4. So if you look at this, I can write this as resultant is going to be this is equal to A11 multiplied by A22, A33 minus 4 into 0 minus 2 multiplied by it is 0 into A33 minus 0 into 4 minus this is plus 3, it is 0 into 0, A22 into 0. So you can see that this is 0, this is 0, however this is 0. So answer is going to be A11, A22, A33. We'll go to the eighth property. Eighth property says that if A is singular, then it is the determinant of A is 0. If I have to say that a matrix is invertible, I can take an inverse of a matrix. That means the determinant should not be, determinant of that matrix should never be equal to 0. For example, we'll take a singular matrix which is A, B, C, D. It is not invertible because for a singular matrix, this AB minus BC will be always equal to 0. So therefore, the matrix is not invertible. The determinant of AB is the product of determinant of A times the determinant of B. Let me say that I have two matrices A and B. A is defined as A, B, C, D, and B is defined as U, V, X, Y. And I multiply these two matrices, I am going to get another 2 by 2 cross 2 matrix whose elements are AU plus BX and AV plus BY. And the elements here are CU plus BX and here it is CB plus D1. And I take a determinant of this, I am going to get the answer as dxCV plus AUDY minus BCUY minus ADVX. That is on the left hand side. Now let me take separately determinant of B and the determinant of A and determinant of B. Determinant of A will give me AD minus BC. Determinant of B will give me UY minus VX. I am going to multiply these two determinants. When I multiply, I get ADUY plus BCVX minus BCUY minus ADVX. This is on the right hand side, and you can see that your left hand side values are equal to the right hand side. Corollary says that determinant of A inverse is equal to 1 divided by determinant of A, because we know that A into A inverse will give me I, and the determinant of A into A inverse will be equal to determinant of I. So therefore, we can say that determinant of A inverse is equal to 1 divided by determinant of A. We will try to apply these properties to solve some problems. Here it says that a square matrix A is given whose order is 3, and also one more data is given to us, that is determinant of A is given as 6. We need to find out determinant of A multiplied by adjoint of A. Let us use the property 9, which says that A into adjoint of A is always given by determinant of A multiplied by determinant of adjoint of A. And here we know that the determinant of A is given as 6, and the determinant of adjoint of A is always given by determinant of A to the power n minus 1. Here n value is equal to 3, so this gives you 6 multiplied by, it is 6 to the power 2. That is 6 multiplied by 36, that gives you 216. And the second problem is we have to find the determinant of 2A. In general, we know that k into A is given by k to the power n into determinant of A. Here it is k is, in this case it is 2 and n is 3 multiplied by 6. So 2 to the power 3 is 8 multiplied by 6, that gives you 48. Next property says that transpose of A has the same determinant as A itself. That means determinant of A transpose is equal to determinant of A. Let us take an example here. Let us take A is equal to, the matrix is given by A, B, C, D. Now when I take a determinant of A, I am going to get this as A, B, C, D is equal to AD minus CD. Now let me take the transpose of A. A transpose is defined as A, C, B, D. And if you take the determinant of A transpose, we get this as AD minus BC. So we can say that these two values are same. So it is as good as writing this as determinant of A transpose is determinant of A. We will take one more example. The determinant of the matrix given here, minus alpha square beta alpha gamma alpha, alpha beta minus beta square gamma beta, alpha gamma beta gamma minus gamma square is equal to 4 times alpha square beta square gamma square. In the first row, if you see, alpha is common, that alpha is taken out, so we have minus alpha, beta, gamma. In the second row, the beta is common, so that beta is taken out, so we are left with alpha, minus beta and gamma. In the third row, gamma is common, so gamma is taken out, so we have alpha, beta and minus gamma. Now in the first column, if you see here, alpha is common. So alpha is taken out once again, so we get alpha square. So minus 1, 1. And in the second row, beta is common. So it becomes beta square. So we have 1 minus 1, 1. In the third row, if you see, gamma is common. So gamma is taken out. So gamma square, it is 1, 1 minus 1. So we have alpha square, beta square, gamma square. So that will be equal to, when I take a determinant of this, I am going to get this as alpha square, beta square, gamma square multiplied by, it is minus 1, minus 1 into minus 1 plus 1 minus 1. So minus 1, it is minus 1 minus 1, then plus 1. So we have here 1 plus 1. So this gives you 1 minus, this is 0, and this is minus 1 minus 1. You get this as minus 2 minus 1, so you get plus 2. And here you get plus 2. So I can write this as alpha square, beta square, gamma square multiplied by 2 plus 2. That will give you 4 times alpha square, beta square, gamma square. A, B, C are the constants. They are all different. And we have been given one more data, that is determinant of A square 1 plus A cube, B square 1 plus B cube, C square 1 plus C cube is equal to 0. We need to prove that ABC is equal to minus 1. Let us consider the determinant, whatever is given to us, and we'll apply the linearity property and split into two matrices, determinant of two matrices, A square 1, B square 1, C square 1 plus determinant of A square A cube, B square B cube, C square C cube. We'll retain the first matrix determinant as it is, and the second one, we know that the common factor here is A in the first row, that has been taken out. In the second row it is B, and the third row it is C. So it is ABC, determinant of 1A square, 1B square, 1C square. The entire thing is equated to 0. Now we will interchange the third column and the first column. When we interchange the third column with the first column, we get this as it is. This determinant will remain as it is. And here when we interchange, it becomes minus. Minus ABC, A square, B square, C square, ABC, 1, 1, 1, that is equal to 0. Further, I will make column exchange here. Second column is exchanged with the first column. When I do the exchange operation, interchange operation, I have to multiply with minus 1. So it becomes minus 1 whole square. And now I can write this as 1 plus ABC multiplied by the determinant of the matrix A square 1, B square 1, C square 1. So if I do some modification, row modification, I am going to get, I retain the first row as it is. I am going to subtract the first row from the second row. So B minus A, B square minus A square, 0. And C minus third row from the first row from the third row. So C minus A, C square minus A square is equal to 0. When I simplify this, I know that I am going to get 1 plus ABC multiplied by B minus C, C minus A, C minus B. But these terms cannot be 0 because A, B, C are of different values. So only A1 plus ABC can become 0. Therefore, ABC is equal to minus 1. Thank you. In the next video, we will study permutations and cofactors.